So, we have discussed about 4 different engines and their efficiencies: Carnot engine, Stirling engine, then gasoline engine and diesel engine, out of which 2 engines are external combustion engines, which are like Stirling engine and no, Stirling engine is the only one that we have discussed, and actually Carnot engine is not even a real one. So, it is an hypothetical one, and gasoline engine and diesel engines are the internal combustion engines. We have discussed about the efficiencies of those. However, there can be many other possible engines or possible thermodynamic cycles that we can construct and calculate their efficiencies. But the important thing is that the Carnot engine, which is a hypothetical one, we can show that no heat engine operating between 2 given thermal reservoirs means basically having a fixed temperature, can be more efficient than the Carnot engine operating between the same 2 reservoirs. So, that means, if an engine runs between 2 fixed temperature reservoirs, then the efficiency of any of those engines cannot be more than the Carnot engine. So, that is what we are going to discuss today. So, let us take about, so you know that all real engines are irreversible engines, right. So, let us take an example of an irreversible engine and an example of a Carnot engine. So, typically the way we construct the process is that we have a high temperature reservoir from which a heat QH is taken. Let us say it is QH prime and a QL prime is ejected to the low temperature reservoir. So, this is an irreversible engine and therefore, I put I as the indicator of that, and let us say the work output of this particular engine is W. So, the efficiency of this engine eta I will be 1 minus QL prime by QH prime. As I said, in all these cases we are just taking the modulus rather than the sign. So, it will automatically come to be that. Let us take a Carnot engine within the same temperature difference. And let us call it E, which we have been defining as E. Here also a different amount of heat is taken in, let us say same work output is given in, and a different amount of heat is ejected out. So, efficiency of this particular engine E, which is a Carnot engine, is 1 minus QL by QH. Now, let us say for the argument's sake that efficiency of the irreversible engine is greater than that of E, say. So, in that case what it means is that 1 minus QL prime by QH prime is greater than 1 minus QL by QH. So, or to write in a different way, we can say that the efficiency of this engine irreversible engine is the work output by the heat input QH prime. Let us say it is greater than that of the Carnot engine. So, automatically we can see. So, remember that we have adjusted the heat input and output in such a way that the work is same. Okay. So, you can always do that. We have kept the work same, but efficiency is different. So, now efficiency I have written in a simpler form. W is the work output, which is of course QH prime minus QL prime, and the heat inputs are different. Now, once I put it like that, you can clearly see that here the QH prime is, since it is greater, QH prime should be smaller than QH, if the efficiency of the irreversible engine is higher than that of the Carnot engine. Okay. Now, let us see that if that is the case, what is going to happen. Now, let us combine the irreversible engine and Carnot engine in such a way that the irreversible engine should drive the Carnot engine. That means, the work that we are going to get out of this irreversible engine should be helping the opposite of the engine. Okay. So, we are going to put this particular engine in reverse and this is in the forward direction. Now, let us do that. So, again TH going to take QH prime heat is going to produce W amount of work and going to throw away QL amount of heat to the low temperature reservoir. This W amount of work now is going to go into the Carnot engine, which is kept in reverse. So, call it R. The exactly opposite of this thing will happen here, which means that QH will go back to the high temperature and QL is going to be taken in from the low temperature. Just the opposite. When you put, so whenever you want to put an engine in reverse, first construct the engine and then just reverse it. So, exactly the signs will be reversed. So, here like QH is positive, W will be negative and then QL is negative. Here QL is positive, W is positive and QH is negative. Okay. The arrows also indicate. So, now see, none of this is till now violating any of the laws, because the heat is transferred from low temperature to high temperature with the help of the work. Okay. So, I have maintained the efficiencies of this engine and efficiencies of this engine, everything is maintained. Now, the combined system is such that coming out as that so QL prime is getting thrown away and QL is taken in. So, QL minus QL prime heat is taken in from the low temperature, and without work being done, QH minus QH prime is thrown in, right. Now, we know that from this construction of the engine, we know that QH prime minus QL prime is equal to W. We know from this engine is that QH minus QL is W. Equating them together, we get QH QH prime minus QL prime is equal to QH minus QL, and therefore, QH minus QH prime is equal to QL minus QL prime. So, which means that I can call it Q and this also will be Q, they are equal, which means that the heat is taken in from low temperature reservoir and thrown into the high temperature. See, sign is very important, because if it turns out that heat is flowing from high temperature to low temperature reservoir, then there is no violation of the second law of thermodynamics. So, it is important that this is a positive quantity that is taken in from the low temperature, and this is a negative quantity that is thrown into the high temperature, and that is what is happening, because we know that the way we have done this, that this is a positive quantity, right, because we have seen that QH, you look at this one now. So, QH is larger than QH prime. So, therefore, a positive amount of heat is thrown into the high temperature reservoir. So, now this is in violation of Clausius second law theorem, right. Clausius statement of, so this is a violation of Clausius statement of second law. Okay. So, which means that our initial argument that an irreversible engine can be higher than a reversible engine cannot be true, because it would have, if it were true, then it would have violated the second law of thermodynamics. So, that means no irreversible engine can have higher efficiency than a reversible Carnot engine. Now, question is that can one reversible engine be better than other reversible engine? Now, we are going to say that. So, corollary to this earlier argument is that all reversible engines working between two temperature reservoirs have the same efficiency. Now, how do we arrive at that? So, remember our construction was like this, that we have a high temperature reservoir from which an engine was taking in heat and throwing away heat, and with that we have added an engine in reverse which took the heat from low temperature and threw into the high temperature. Okay. Now, we said that let us say in this particular case now we have both of them as reversible engine. Let us call it R 1 and let us call it R 2. Of course, R 2 is added in the opposite direction. Okay. So, here R 1 is driving R 2, just like the way we have constructed it before. Now, following the same argument, we can show that eta R 1. So, we have what we have gathered from last example, that eta I cannot be greater than the reversible one, which means it will be either less or equal to the reversible one, the one on the right hand side. Similarly, following the same argument, if we put it that way, we can show that eta R 1 cannot be greater than the R 2, for the same reason that an irreversible engine was not being able to drive that. So, it cannot R 1 cannot be greater than R 2. Now, let us switch the places of R 1 and R 2. So, this left hand side becomes R 2, which will drive now R 1, and we can, because there is R 1 and R 2 arbitrary, eta R 2 cannot be greater than eta R 1. Now, you see when you combine both of them, that there is only one possibility that exists, that eta R 1 is equal to eta R 2, which means that all reversible engines will have the same efficiency. If it did not be the case, then let us say if one of them is less efficient, what will happen is that if one of them is less efficient, we are going to put it on the right hand side and try to drive a reversible engine, which you know will actually violate. So, so now we see that the all reversible engines working between two temperature reservoirs have the same efficiency. So, that is very important. Efficiency, when you are talking about, we are only talking about the engines which have same fixed to temperature from which it is taking in the heat and throwing away the heat. However, in case of diesel and gasoline engine, we have seen that is not the case. For diesel engine, we had all 4 different temperatures, and in the gasoline engine also we had different temperatures. However, for Stirling engine, we saw that if using the regenerator, it was maintaining only 2 different temperatures, like the upper plate and the plate below, and therefore, it could have as close to real Carnot engine as possible.